I hope the screen is also visible to you. Is it? Is it? Please give me a confirmation, so that. Okay, thanks. Then I shall start. It's 6 o'clock already. Hi everyone. So this is going to be the first weekly live session of the course on remote sensing, principles and applications. A course brought to you by NPTEL and the SWAM initiative. I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme at the Interdisciplinary Center for Water Research at IISc Bangalore. And this course has been taken by Professor Ishwar Rajshekharan from the Department of Civil Engineering at IIT Bombay. First of all, I will just like to clear a few things. All the video recordings of these live sessions conducted by me will be made available on our YouTube channel. I will be sharing the link of that YouTube channel as well as the links of the videos pretty soon. The files which are relevant to the weekly live sessions taken by me will also be made available through a Google Drive folder. The files and the video recordings will be made immediately available after the class. Probably not the case for the first weekly live session, but from the next live session onward, after next Friday, you will definitely be getting both the files as well as the video recordings immediately after the class ends. And finally, all the images which I'm going to show here are basically taken from internet or from some books, and that's only for study purpose. We are not trying to plagiarize or copyright something. So the first weekly live session, I thought we would be I could just be discussing a few questions which would be relevant to the first assignment of yours, which is content from the first week. I made a set of questions out of it, and let's try to discuss and solve them. Someone is trying to enter, I guess. Okay. So the first question is a very easy one. The remote sensing of observing the amount of solar radiation reflected by the object of interest is active remote sensing, passive remote sensing, sonar, or all of the above. What do you think, guys? Please feel free to unmute yourself and answer. Any comment, any reply, anything?
Active.
Sorry, someone is again trying to enter. Yeah. Kindly unmute yourself. In case you're not replying, then please. Yeah. Thanks. So the first question is about the remote sensing of observing the amount of solar radiation reflected by the object of interest. So what is the basic difference between the two fundamental types of remote sensing methods? Remote sensing can either be remote sensing can either be through active remote sensing processes or passive remote sensing processes. Someone is again trying to enter. Are you guys able to admit someone? Whoever enters here. I believe you guys also have that authority apart from me. Okay. So there are two types of remote sensing setups. The first one is an active remote sensing setup, and the second one is a passive remote sensing setup. And we all know remote sensing is nothing but extracting information about an object or a phenomenon without being in actual touch with it. We are not touching it, but we are gaining knowledge about it, being at a particular distance from them. So just a brief knowledge about it. Remote sensing is gaining information about an object or phenomenon. Object in the sense, let us say we want to know about the buildings, how tall, how wide the buildings are, or phenomenon. Let us say we want to know how are the evapotranspiration dynamics from a particular ecosystem. So it gives you the knowledge or information about an object or the phenomenon without being in touch with it, without being in touch with it. You're not actually touching it, you're not actually going to the site to measure it like that. So through some indirect approaches, probably utilizing the exploiting the electromagnetic radiation properties, you are getting to know about the information or the knowledge about the object or the phenomena. Now there are two fundamental uh, cases in remote sensing based satellite information. One is the active remote sensing, the other one is passive remote sensing. So in the passive remote sensing, we are utilizing, or I mean, we basically the satellite tries to detect some reflected source of emission. Of radiation, which is not produced by itself, not produced by itself. Whereas in the active remote sensing part, the source of radiation is own. Source of radiation is own. Let's take another slide just to explain this basic. Someone again trying to enter admit. Yes. So active remote sensing is the one in which own source, and passive remote sensing is the one in which it would detect reflected radiation from another source of radiation. So any idea, I mean, what may be a possible source of emission, which I mean, which we all know about, which we all see probably every single day? Any idea? Please feel free to comment. Feel free to unmute yourself and give some, I mean, comments on it. Anything you want to comment on that? What can be a possible passive remote sensing based framework? Any idea? Okay, no issues. I will proceed then. I will tell you. So mostly the passive remote sensing based frameworks utilize the reflected energy which was actually emitted from the sun. So this is our sun, let us say, and this is the landscape. Some, I mean, sun is a massive source of energy, everyone knows that. And this radiation, after let us say it gets reflected from the land surface, would be detected by a satellite. So such systems are basically the passive remote sensing based systems. They are not emitting their own source of radiation, they're utilizing something which is not their own. Okay. Whereas active remote sensing, they have their own source. They let us say, suppose they emit something on their own to the land, and then they detect the reflected wave to give some information about the body or the object or the phenomenon. So the common type of active remote sensing based satellite systems are, I mean, mostly microwave based systems. I mean, one of them you may be knowing is radar, which is radio detection and ranging. Another one is lidar, that is light detection and ranging. Another one is sonar. Sonar is basically sound navigation and ranging. So what do we do in that? I mean, let us say you are you are utilizing sonar. So you have a ship, okay, you would be emitting some sound waves, let us suppose, to detect whether there are some submarines, hidden submarines in the sea. Okay. And the same reflected waves will be again detected back by the boat. Let us say it's a boat or a ship. So they would detect that how much the distance of the submarine is from the boats through the time which is taken by the sound waves to travel to and back from the hidden submarine. So that is how they will get to know that. Radar and lidar also use more or less the same mechanisms. The only difference is that they don't use sound waves for their detection. They use microwave waves. Now, about passive remote sensing based sensors, they use mostly, in most of the cases, they use the energy which is emitted from the sun, and they use a reflected energy from any particular body, object, or a phenomenon to detect the reflectance in most of the cases. So the most common passive remote sensing satellites, which are regularly used by remote sensing enthusiasts worldwide, are QuickBird, then Landsat. Landsat is an iconic satellite, by the way. It is now well over 50 years in application. I mean, through its different versions. And recently, it is also MODIS. MODIS is Moderate Resolution Imaging Spectroradiometer, a very important satellite type, sensor type, which uh, kind of gives you a knowledge of ecosystem dynamics, the likes of, let us say, carbon cycle components or water cycle components like evapotranspiration, or even the emissivities or the land surface temperature. So it gives a range of products. This is basically moderate resolution imaging spectroradiometer. A very Nowadays it is one of the very popular satellite system. By the way, Landsat is iconic, literally iconic. It is in use for over the past 50 years. So if you want to know, let us say, the landscape of uh, 1980s, you can just go to the USGS website. USGS is United States Geological Survey website, and you can download Landsat images free of cost, which are available at a resolution of 30 meters. By resolution, I mean that the pixel size, the smallest size is the pixel, and the pixel size is 30 meters. So you can get to know how a landscape evolved over the time through Landsat kind of a satellite system. Why? Because it has been used for over 50 years, and 50 years is a lot of time to detect that. Let's move on. The second question is, so what would be the answer? First of all, the remote sensing of observing the amount of solar radiation reflected by the object of interest is A, active remote sensing, B, passive remote sensing, C, sonar, or D, all of the above. So what would be the answer? Any guess? Anything you want to say? The answer would be B, passive remote sensing. Basically, active remote sonar is also a kind of an active remote sensing system itself, as I discussed in the next slide. And passive remote sensing detects uh, mostly solar radiation itself, as I illustrated in this slide. Now, question number two: which of these is not an example of remote sensing? A, capturing a photograph using a camera. B, detecting planes using a radar. C, checking the temperature of water using a thermometer. Or D, listening to announcements in an airport. So remote sensing can either be audible, it can be visible, or it can be even in the uh, infrared range or microwave range, which are not quite visible to human eyes. So the fundamental definition of remote sensing states that we the information is extracted about a body or a phenomenon without being in touch with it. Sorry. So in option number C, we are actually touching the water. I mean, to detect its temperature using a thermometer. So this can definitely not be an example of remote sensing, and the answer has to be C. Let's just understand the other options also. Capturing a photograph using a camera. So what exactly is happening? Uh, uh, a camera can either work with flash, the flash system, or it can work uh, through passive remote sensing pathway. I mean, when you detect the solar radiation, or let us say an artificial radiation which is reflected back from, let us say, a tube light in your room. So whenever you see anything in the room, whenever you, let us suppose, you are seeing uh, a photo in front of you, how do you actually see that? You are basically observing nothing but the reflected radiation coming back, reflected waves coming back from, let us say, tube light in your room right now, or the solar radiation in case it is daytime. So that is how you are actually able to see an image. The camera is also effectively doing the same thing. It is either by flashlight uh, detecting the reflected wavelength to produce an image, or it is also in case of daytime, if you are not using a flashlight, then it is basically detecting the reflected solar radiation. So that is the option A. Option B is detecting planes using a radar. The radar again is a very well-known remote sensing system. We discussed it in the previous question itself. And option D is listening to announcements in an airport. So it is a kind of an audio remote sensing based system. So someone is blurring it out. Someone is basically announcing it from the vocal cord, and the wavelength, the sound waves are being propagated, and they are being detected by the eardrums, and that is how you get to listen to the announcements in an airport. So this is also effectively a remote sensing based system which is being employed by the human beings itself. So let's move to question number 3. The bands of electromagnetic spectrum where the object is fairly transparent and allows to see the earth are known as A. Transmission bands, B. Atmospheric windows, C. Absorption bands, or D. Transparent windows. Uh, okay, so the answer is definitely atmospheric windows, but I will explain it why. I mean, what do they actually do? I will explain it. So atmospheric windows are basically the range of wavelengths where energy can pass through from the atmosphere into the surface. So the range of wavelengths. Someone is trying to enter again. Leave. Through which the energy can pass through. Okay, so there are two basic kind of interactions of the radiation with that of the atmosphere. One of them is the uh, absorption, the other one is scattering. And atmospheric windows primarily deals with the absorption phenomena itself. So most of the atmospheric particles, let us say, like the likes of nitrogen, oxygen molecules, or the dust or the clouds, they block some of the segments of wavelength range uh, from going into the land surface. And through that, you cannot detect anything. As a remote sensing scientist, you cannot detect anything if the wavelength is already blocked. So those wavelengths for which there is not blocking, I mean, there is no considerable blocking of the wavelength, and through which you can detect something useful as a remote sensing based scientist, those are known as atmospheric windows. Now this window, as I told you, would be dependent on several factors, dependent on clouds, because clouds can cause a massive amount of blockage. I mean, when you are I mean, of the solar insolation, the solar radiation can get blocked from coming into the land surface by the clouds. They can also get blocked by water vapor. Water vapor is a prominent gas, greenhouse gas in the atmosphere, or even some trace greenhouse gases. GH, sorry, greenhouse gases, GHGs, and of course the components of the atmosphere like dust or anything else. Nitrogen, dinitrogen, anything, dinitrogen or dioxygen, these kind of molecules can also block it. So the kind of implication, the major implication can be on the energy budget of the Earth. Uh, so the major benefit out of this course of remote sensing is that it is an all-encompassing course. People from hydrology, people from transportation engineering, people from geotechnical engineering, people from even social sciences or earth sciences can utilize it for the research. So it is a very broad course, by the way, and that is its usage. So I will try to give its applicability of the atmospheric windows for people who evaluate the energy budget of the Earth. So what can be its implication for the same? I will take another slide to explain that. Okay. Earth's energy budget. One of the applications, major applications for people who deal with such scenarios, deal with such research, can be on the Earth's energy budget. So the total solar irradiance means the incoming solar radiation, basically. Okay, at the top of atmosphere over a long period is found to be nearly around 340 watts per meter square. So out of it, only around 200 watts per meter square reaches the surface, the land surface, via windows. The windows, which are mostly in the optical range and infrared range. Optical range is primarily zero point 0.4 micron to 0.7 micron. The range which can be detected by human eyes, that is nothing but the optical range. So this is the sun. This is, let us say, the land surface. These are clouds. This is the atmosphere. So this the numbers basically state that at the top of the atmosphere, which is TOA, let us suppose I denote it by TOA, around 300 watts per meter square of total energy is basically received. But at the surface, only around 200 watts per meter square will be received. So why this discrepancy? Because something is being absorbed by the atmospheric constituents also, like dust particles, clouds, or even the water, the molecules, the water vapor, or the trace greenhouse gases. So they are kind of absorbing some parts of it. I mean, something is happening in between, and that absorption is the reason why our detection of remote sensing based knowledge cannot be fulfilled for each and every wavelength range. We can only be limited. We are basically limited or constrained by this atmospheric window. I mean, we can only detect particular information about the land surface only through a very narrow atmospheric window, which is primarily, luckily in the visible as well as infrared range of electromagnetic spectrum. Okay, so let's move to the next slide. Next, yeah, did I write the answer? Yeah. How do we call the wave portion of the electromagnetic radiation spectrum spanning from 0.75 centimeter to 1 meter? So the electromagnetic radiation spectrums have been given names based on their wavelengths or frequencies. And the wavelength and the frequency are limited through C equal to nu lambda equation, where C is the speed of light or the electromagnetic radiation, which is 3 into 10 power 8 meter per second. So C is basically a constant. So nu and lambda, this product is basically a constant. Nu is the frequency, or in general the number of cycles per second, and lambda is a wavelength. Okay, so it can be said with surety that as nu and lambda are inversely proportional. So if the frequency increases, the wavelength will be less, and vice versa. So how do we call the wave portion of the electromagnetic radiation spectrum spanning from 0.75 centimeter to 1 meter? This is primarily in the microwave range, as you can see here. So it is microwave range. Visible is primarily from 0.4 micron to 0.7 micron. The lower wavelength is primarily the blue wavelength. The larger wavelength is primarily the red wavelength, and it has its own implications. I will explain it through another question, which would be in due course of time. So the larger wavelengths behave very differently with respect to the atmosphere versus that of the smaller wavelength visible rays. So the blue light will behave very differently from red light. I will explain it. Now let's go to the next question. The total amount of energy emitted by an object at a given temperature is given by which law? So there are some fundamental laws which are essential for a thorough knowledge of remote sensing, of the course of remote sensing. The first three options, the Stephen Boltzmann law, the Wien's displacement law, and the Planck's law, are the three most basic laws of remote sensing. By the way, Lenz law is something entirely different. It deals with the magnetic and the electric wave interplay. So this has nothing to do. For this course, this has nothing to do with our interest, Lenz law. But the laws which are written in the first three options are pretty important. So, in short, if I just want to give the answer to this question, the answer would be, okay, someone is trying to enter again. Okay. So the actual answer would be the Stephen Boltzmann law, because it links the energy emitted by an object with respect to the temperature. But I will be explaining each of them in details. But I will firstly start with the Wien's displacement law, and I will try to give an overview about each of these laws, by the way. So Wien's displacement law states that the peak, the wavelength peak happens at a particular temperature. They're related like this: B is a constant, and T is the absolute temperature, means the temperature in terms of kelvins. Okay, so let us suppose you are trying to find out the intensity versus wavelength lambda. So the plots for different temperature ranges would look something like this. For lower lambda, so this would be, let us say, the visible So lambda max, from this equation we get to know that lambda max is inversely proportional to T. So as lambda max increases, T decreases. So this visible is basically the amount of temperature which is present in the sun, which is around 3000 to 5000 Kelvin, whereas this 300 Kelvin is the temperature of the Earth. So the wavelengths, the wavelength peak will happen at a larger wavelength for Earth than that of a sun, that is a visible range. So that is what the Wien's displacement law states. Now, how do we actually derive it? The derivation is extremely cumbersome, but I will just give you an idea. it is basically linked with the Planck's law, which is again a very fundamental equation of this remote sensing course. So the Planck's law is like this. Here h is the Planck's constant, which we all know is 6.63 into 10 to the power minus 34 joules second. C is the speed of light in vacuum, so that is around 3 into 10 to the power 8 meter per second. Lambda is the wavelength, K is the Boltzmann constant, which is again a fundamental constant. T is the temperature. That's it. So U lambda is basically the black body spectral radiance. Black body spectral radiance. I will take another slide to explain it. And it illustrates that the power, this U lambda, would give us the power per emitting area per the projected solid angle. Anyways, so let us go back to that equation. What will happen if I take the first derivative of it? If I take the first derivative and we equate it to 0 with respect to the wavelength, then we will get the wavelength corresponding to the peak power per emitted area per solid angle for that region. So we do the same. Let us try to do that. We are taking the first derivative, so we are basically conducting a test for the maxima. The derivative would look something like this. It would be very cumbersome, by the way. So this is the derivative. This is a very large expression, by the way. So when you simplify it, you will get something like this. Now we try to define another variable. Let us say x as hc by lambda kt, and you then solve it further. You will get x equal to 5 1 minus e to the power minus x. You solve it, you will get the lambda peak as equal to hc by x kt, which would be around 2.897 millimeter Kelvin by temperature, which is again in Kelvin. So this would be the final way through which you can get the derive the Wien's displacement law. Anyways, this derivation is not important for you. I mean, at this stage, I just wanted to show how we came to this expression from the Planck's law. Planck's law is a fundamental equation in governing equation in this domain, by the way. I'll take another slide. Now, I mean, the question also stated something about the Lenz law. I will just write a brief about what this Lenz law is. Sorry. So Lenz law states that the electric current direction induced by a conductor conductor by changing the magnetic field. So this course doesn't have a lot to do with Lenz law, by the way. So we can just exclude that, but I will just write it for your own reference. Electric current direction induced by a conductor. You might have read about it in somewhere in class 12th probably. By changing magnetic field. And the last law which was stated in this question was the Planck's law. Planck's law, as I told you, is the fundamental governing equation in this course, by the way, this part of the course. So Planck's law is that states that electromagnetic radiation from heated bodies means anything with temperature. Even the human body is heated. It is at a 37 degrees Celsius temperature. Is not emitted as a continuous flow, but is made up of discrete units which are known as quanta of energy. So this is what the statement of Planck's law states, by the way. I will just give you a very brief instruction which I forgot to give you. So some of the people who have worked with Google Meet, I mean, in recent times, they have speculated that Google Meet only allows for a 1 hour meeting. I mean, if we extend a 1 hour duration of the meeting, then Google Meet will probably remove us from the meeting link. So, if any one of you gets removed from the Google Meet link, please feel free to use the same link, and you can enter the room again. So this might happen at the 1 hour mark. We are around 20 minutes from that 1 hour mark currently. But if anyone, uh, I mean, if somehow the Google link, Google Meet does not work for you, please feel free to use the same link to enter the room again. Okay, so let me write the expression in the next slide. So I am writing the same expression of the Planck's law, which we use to derive the Wien's displacement theorem, displacement law. So 2hc square by lambda to the power 5 by 1 by e to the power hc by lambda kt minus 1. So this is the same expression, by the way, where h is the Planck's constant, which is equal to 6.62 into 10 power minus 34 joules second, and k is something known as the Boltzmann constant. They are fundamental constants. 1.381 into 10 power minus 23 joules per Kelvin. So this is the Planck's law. And the Stephen Boltzmann law, basically the one which is actually asked in the question, is also basically derived from the Planck's law itself. So Stephen Boltzmann law is like this: U by A. Is someone trying to enter again? Getting an audio message. Yes. Is equal to sigma t to the power 4. So this states that for a black body, so the Stephen Boltzmann law is stated only for a black body, and U by A is nothing but the amount of radiation which is emitted per time from an area A of black body at temperature T. So the fundamental inference from this Stephen Boltzmann law is that the amount of radiation is amount of radiation emitted per time from a body would be directly proportional to the fourth power of the temperature. So more the temperature, more would be the emittance. It's emitted radiation. So that is the fundamental inference, and that is for a black body. What happens if it is not a black body? Then we would be using a correction factor, which is known as the emissivity. I will be taking one more slide to explain that. What's happening here? Yes. So the Stephen Boltzmann law states that for a black body, the emitted radiation U will be nothing but sigma A T to the power 4, where sigma is a fundamental constant known as the Stephen's constant. It is 5.67 into 10 power minus 8 watt per meter square per Kelvin power 4. Okay, and in case I will give you a very interesting trick. If you are finding it hard to memorize this constant, in case it's not given in the exam, it's very easy to memorize it, by the way. It is 5, 6, 7, 8. All of them are in the, all are basically consecutive numbers, and all of them are in this constant. So it's very easy to memorize. Anyways, so if the object is not a black body, someone is trying to enter again. For a black body, it is very straightforward. The emitted radiation would be sigma A. A is the area times the fourth power of the temperature of the body. And if it is not a black body, then it would be U equal to E sigma A times T to the power 4, where E is something known as the emissivity. And it will lie from 0 to 1. It will be between 0 to 1. So ideally the emissivity would be the highest for the black body. Black body is a completely idealized situation, and no body, no surface can be no surface can be a black body actually in nature. Okay, so black body is completely hypothetical perfect absorber which absorbs everything, or radiator with zero reflecting power. The reflecting power is absolutely zero. That is the case with a black body. Okay, so through it we got to know that there is something called the Stephen Boltzmann law, and it links the emitted energy with respect to the temperature, and the correspondence is basically the fourth power of temperature. So the original question was the total amount of energy emitted by an object at a given temperature. Uh, Which law to use for that? It is definitely the Stephen Boltzmann law. I will take another case just to illustrate about the Stephen Boltzmann law. Yes, I will take another slide to explain that. Let the surrounding temperature be surrounding temperature of the body, something known as T naught. So that the the Stephen Boltzmann law, according to that, we can use that the net energy radiated by an area A per unit time would be, let us say, delta U, which is equal to U minus U naught. That is the original temperature of the body minus the temperature, temperature from the surrounding objects, and you have to apply the Stephen Boltzmann law on it. So it would be the emissivity E times sigma A times T to the power 4 minus T naught to the power 4. So this would be the net energy radiated. Again, this Stephen Boltzmann law, just like the Wien's displacement law, is also uh, produced by integrating the Planck's law itself. The Planck's law is the governing equation. So uh, this law is also basically derived from the Planck's law itself, but this would be too tedious to, out of scope of this course, so I will not be illustrating it here for the time being. The next question is that the radiation from the sun is, what kind of polarization is it? Okay. So what is polarization? Polarization, what is that exactly? Polarization is mostly used for microwave remote sensing based procedures. Uh, it states the direction of electromagnetic fields produced by the antenna as energy radiates away from it. Okay, so this is the fundamental knowledge about it. So one basic takeaway from this is that the way an antenna is basically planted or mounted would affect the polarization, whether it's circularly polarized, whether it's linearly polarized like vertical or horizontally polarized, or elliptically polarized. It will be affected primarily by the antenna mounting position. So let me write it in the next slide. The way an antenna is mounted affects the polarization. Okay. Now let's look at some of the polarization scenarios. So the two primary linearized polarization scenarios are the vertical and the horizontal polarization cases. Someone is again trying to enter. Yes. So as written in the text, vertical polarization refers to the oscillation of an antenna's electric field on the vertical plane, whereas horizontal polarization refers to the oscillation on the horizontal plane. So that is the basic difference. It is defined by the orientation of the electric field with respect to the planes. So if the oscillation of electric field is on the vertical plane, then it is vertical polarization, and vice versa. And for the case of horizontal polarization, the oscillation of the electric field should be on the horizontal plane. And we know very well that the directions of the motion of the electromagnetic wave, the direction of the electric wave, and the direction of the magnetic wave for any electromagnetic wave system is primarily mutually perpendicular. So giving the direction of the electric wave itself will give an idea about the direction of the magnetic wave primarily. So vertical is the one in which the oscillation of electric waves happens on the vertical plane, horizontal when the oscillation happens on the horizontal plane, and slant is also a linearized kind of a polarization, but in this case it is not either entirely vertical on the entirely vertical plane, or on the entirely horizontal plane. So this is something known as the slant polarization, which is depicted in the third diagram of the left figure. Then coming to circular polarization, to explain it well, circular polarization, as I'm just reading it from the text, circular polarization or CP refers to a radio wave that rotates as the signal propagates. When it rotates to the right, the polarization is referred to as right hand circular polarization. When it rotates to the left, it is referred to as left hand circular polarization, LHCP and RHCP. Many of the GEMS multiband antenna products are circularly polarized. GEM is basically a company from which I've basically used this text. So they produce multiband antenna which are primarily circularly polarized. So let's look at it. The okay, when it rotates to the right, when the radio wave rotates and okay right, the signal is known as right hand circular polarization. Is it the case? Yes, exactly. It is rotating to the right. I mean, always see the direction. Okay, and in the case of left hand circular, it is rotating to the left. So it is this LHCP on the right. I mean, right side of the image versus RHCP on the left hand side of the image. There is another kind of polarization which is the elliptical polarization. An elliptical polarization refers to an electrical field that is propagated in an elliptical helix. Similar to circular polarization, elliptical polarization can either be right-handed or left-handed, just like the way it gets rotated. So these are the two elliptical polarization based diagrams. The right hand elliptical on the left hand side of the slide, I mean downward left hand side, and the left hand elliptical on the bottom right of the slide primarily. Okay, so what would be the radiation from the sun, whether it's circularly polarized, whether it's vertically polarized, or whether it's horizontally or randomly polarized? Any idea? I mean, what can it be? Any idea? Please feel free to answer. Any idea or anything? Please, I mean, please don't hesitate in answering. Let's be a bit interactive. No answer is a wrong answer. So please, I mean, if you have any thoughts about polarization or anything which I have discussed so far, please discuss that with me. Or do you want to discuss it at the end of the class? Okay, it's a very quiet class. Okay, I will rather ask for your doubts at the end of the class itself, of the weekly live session itself. In that case, so let me just give the answer straight away. The radiation from the sun is actually randomly polarized. It's a mixture of all. So it is randomly polarized. Okay. Yeah. So we are done with the first six questions. Let's move to something like this. Select all the appropriate answers. Two waves will be perfectly coherent if they are okay. What is coherence? For perfect coherence, we need some rules between two waves. So the waves should have the same frequency, and hence there will be a constant phase difference from each other. It's very easy to understand. So, and constant means does not mean that the phase difference will be zero always. It may be zero, but it may not be zero also. So let us suppose this is one of the waves. There is another wave of the exact same frequency, but there is a phase difference. As you can see, there is a phase difference. So these two waves can be taken as perfectly coherent. So having constant phase difference is definitely one of the answers. This is a multiple correct answer. I mean, kind of a question. So B is definitely correct. What about a monochromatic wave? What is this exactly? Monochromatic. Someone is trying to enter. So monochromatic is something which, I mean, which has the same color, but colors are also quite arbitrary, right? I mean, the English definition of monochromatic, the English dictionary definition is that it is of the same color. But in remote sensing, we actually don't have any color, I mean, as such, because we detect the electromagnetic spectrum, which is even beyond the visible range of human eyes, by the way. So it should not be defined with respect to the colors of the electromagnetic rays, but it should be defined with respect to the wavelengths. So monochromatic means that they have single wavelength, and mind you, and not single color, and not single color, because color in itself is a very arbitrary thing in this course of remote sensing, by the way. And color is extremely subjective. I will explain it in the next slide, by the way. That is the beauty of this course. And there is another course, another term, collimated. What is collimated exactly? Collimated means that they travel in a single direction. The wave travels in a single direction. So the answers are actually monochromatic. They need to be monochromatic. They need to be having a constant phase difference also. The phase difference may even be zero, and they need to be collimated. Perpendicular is not the answer because they may be off at, I mean, at any angle, by the way. So A, B, and C are the answers to this question, by the way. And with that, I think I now have the time to discuss why I emphasized on the color. I mean, why is there nothing called color in this course of remote sensing? I will discuss it now. Okay, so whatever colors which we are able to see in, I mean, as human beings, they are in the visible range itself. They are primarily from zero point 0.4 to zero point 0.7 micrometer range. That is what we can visualize, visible range. And most of the images which you see on the computer, which are colorful, they have three distinct bands: R band, G band, and B band. That is red band, green band, and the blue band. Blue is the lower wavelength, R is the higher wavelength. Okay, so they amalgamate them all together, they concatenate all together to produce an image, which is the colorful image which you see on a laptop, or on a laptop screens, or on a or on your computers. And that is why they are also known as RGB images, by the way. So they have different discretizations of red, green, and blue colors to produce a singular image. So that is the thing with it. Now, in remote sensing, what we are doing is that our eye is not detecting the wavelength actually. And in most of the cases, in satellite-based remote sensing, the eye is not detecting the reflected wavelength. It is actually detected by the sensors, electrical or electronical sensors, and they have the capability to perceive even wavelengths which are beyond the visible range of human bodies. So they can detect wavelengths much beyond the range, like in one of the questions which I discussed. Yeah, so you can see that the visible range is a very narrow band of wavelength primarily, but these remote sensing based sensors, they can detect things even beyond that. So if you are let us suppose you are detecting radio wave image or microwave remote or infrared image, what will happen exactly? That will not be visible by your human eyes. So what they do is that they choose three arbitrary bands. One of the band may be, let us say, near infrared band. One of them may be, let us say, uh, one green band, and one of them may be again another near infrared band. And then they amalgamate them together, they concatenate them together, and then they produce colorful images, as you see. I mean, uh, through satellites. So they are not actually colorful, but they are made colorful by some manipulation techniques. You will be learning those manipulation techniques and uh, image processing techniques also in this course, but probably 3 to 4 weeks from now. So that is how we primarily build images which are beyond the perception of human bodies, a visible perception of human beings. Let's move to the next question. According to the Doppler effect, when the source and the observer are moving towards each other, wavelength will be what? Okay. Let me write. Yeah. For seventh, the answers, correct answers would be A, B, and C. Now moving to the question on the Doppler's effect. According to the Doppler effect, when the source and observer are moving towards each other, wavelength will A shift towards the longer end, B remain unchanged, C double, or D shift towards the shorter range. Okay, so you might be able to recall that we learned about the Doppler effect for the first time in our class 11th physics textbook. And Doppler effect primarily deals with the cases when the observed. Doppler effect is primarily observed when the source of waves is moving with respect to the observer. So there may be cases like the source is moving. There may be cases like the source is moving and the observer is stationary. There may be cases like the observer is moving but the source is stationary. There may be cases like in which both the observer and the source are moving. So what will happen to the frequency or the wavelength? That is what the question wants to ask. And the question actually has asked the generalized case when both the source and the observer are moving, and that too towards each other. So I will start with the basic definition of Doppler's effect. Doppler effect. It is observed when the source of waves is moving with respect to the observer. So what does it do? It changes the frequency. Definitely it changes the frequency. And if frequency changes, the wavelength will also definitely change of the wave. Why? Because the frequency nu and the wavelength lambda are actually related like this: c equal to nu lambda, where c is the speed of the electromagnetic radiation. Okay, so primarily if nu and lambda are inversely proportional primarily. If lambda increases, then nu will decrease, and vice versa. Okay, so that is what will happen. So let me just give the common Doppler effect equation. So the Doppler effect. Hello, does anyone has question? Any question? Someone has unmuted himself or herself. Any question, Priya? Okay. Okay, so the Doppler effect formula is this. F dash is basically, F is the frequency, V plus minus V naught by V plus minus Vs times F. This is the Doppler effect formula. I will explain what the notations are. F dash is the observed frequency. F is the actual frequency which is emitted from the source. V is the velocity of sound waves V naught equal to the velocity of observer, Vs is the velocity of the source. So we can, I mean, through this there can be different cases. The first case may be, let us say, when the source is moving towards the observer and the observer is at rest. The second case may be that the source is moving away from the observer and the observer is still at rest. The third case may be that the observer is moving towards a stationary source, and the fourth case may be that the observer is moving away from the stationary source. And the fifth case would be a generalized case which the question actually asks you to compute. So let's take that up in the next slide. Okay, so the Doppler formula, I will rewrite it again. Rewrite it is V plus minus V naught by V plus minus Vs times F. Let's take the few basic cases first of all, just to understand, I mean, how it is developed. So case A is the one when the source is moving towards the observer at rest. So the observer is at rest, so that would mean that V0, V naught is 0. So, and source is moving towards the observer. So we will basically deduct it from the velocity of the sound waves. So we will get F dash equal to V by V minus Vs times F. This would be the observed frequency in that case. Let's take another case, case number 2. In this case, the source is moving away from the observer and the observer is still at rest. Okay, so V naught is anyway 0, just like the case A, the first case. So F dash, since they're moving away, so we need to add them up actually. So it will be V by V minus Vs. It is nothing but it is coming from the concepts of relative motion, by the way. Okay, so this will be F dash equal to V by V plus Vs times F. Okay, so we have taken the two basic cases already, case A and case B. Let's take another case. Case C, let us take another case where the observer is moving now. VO will not be 0 anymore. Observer is moving towards a stationary source. So Vs is 0 because the source is stationary. So we just plug it into the equation which was given in the last slide. So it will be V by V plus V naught by V times F. That would be the frequency in that case. Let us take another case. Case D. Observer is now moving away the stationary source. Source is stationary, so Vs is definitely 0. You just plug it into the equation, it will get V minus V naught by V times F. And what does the question actually asks you to do? The question wants you to understand what is the wavelength, not the frequency first of all. wavelength when the source and observer are moving towards each other. So they both are moving, and they both are moving towards each other. So let's take that case as the case number E, just to understand. So we will take that as case E. Source and observer, they are both moving, and they are both moving towards each other. So f dash will be v plus v naught by v minus vs times f. So what do we infer from that? We infer that the numerator is increasing, the denominator is decreasing. So that would mean that f dash would definitely be much larger than f. F dash is greater than f. It is a basic inference out of arithmetics. So if the frequency is frequency of uh, frequency, the new frequency is greater than the original frequency, then the wavelength will definitely be following the opposite relation. So this would basically mean that lambda dash is less than lambda. Why? Because c is equal to f lambda. So f and lambda are actually inversely proportional. So that is why the relationship actually changed from, I mean, when we come from the frequency equation to that of the wavelength equation. So what do we get finally? We get that the new wavelength is actually lesser than the original wavelength. So we observe a shift towards the shorter end. That means that the wavelength is shortening, and that should be one of the options. Yes, so that is basically option D. So option D is correct for this case. I will consider one last question for today, for the day, and after that we will just discuss some basics of this course. I mean, just to have some fun with this course. But yeah, before that, let's discuss this last question from the course. I mean, for today's weekly live session, the question states that the non-selective scattering occurs when the size of the molecule is okay. So they want to know what happens in this scattering phenomena. I mean, non-selective scattering phenomena. What is the relation between the particle size and the wavelength size, basically? That is what this question wants to know. So before that, I will just tell you that the radiation interaction with the atmosphere primarily occurs by two cases. Number one is the absorption, which we discussed in the first and the second questions already. I think probably the third question. Which question was it? Yeah, we discussed it in this atmospheric windows question already. So it was discussed in question number 3. Atmospheric window, it is related to the absorption. And the second one is something known as a scattering, which is another interaction, another way through which the radiation interacts with the atmospheric constituents. So radiation interaction with the atmosphere primarily occurs through absorption, which we discussed in detail, by the way, in question number 3, and also scattering, which is a very major case. And scattering is primarily of 3 types. Number 1 is Rayleigh scattering, second is Mie scattering, MIE, and number 3 is non-selective scattering. And this question asks us about the non-selective scattering itself, but I will be discussing about each and every type. So the first case is Rayleigh scattering. What happens is that the particle size in case of Rayleigh scattering is much lesser than that of the wavelength of the radiation. So what kind of particles may they be? They may be small dust particles, very small dust particles in the atmosphere. They may be the dinitrogen dioxygen molecules also. They're very small in size, mind you. Okay, so the Rayleigh scatter is primarily inversely proportional to the fourth power of the wavelength. The Rayleigh scatter is primarily inversely proportional to the fourth power of the wavelength. So what does it indicate to us? It indicates that when the wavelength is low, the scattering is massive. Why? Because it is not just the first power, it is the fourth power. So it will basically intensify. Okay, so I will explain it in the next slide. So Rayleigh scatter is directly proportional to 1 to the power 1 by lambda to the power 4. So an implication would be that the shorter wavelengths, like blue wavelength in the visible spectra, would get scattered much more than the longer wavelengths like red. So this is why you observe that the color of the sky. Someone is trying to enter again. Let me check. Let me admit him or her. Just 1 second. So it is an implication of the Rayleigh scattering that you observe that the color of the sky is actually blue, because blue has a shorter wavelength in the range of zero point 0.4 to zero point 0.5 micron primarily, and since the wavelength is small, it gets scattered much more, and that is why you see that the color of the sky is blue. It is primarily because of Rayleigh scattering. This question may be asked sometime. Okay. Anyways, the second type of scattering mechanism is the Mie scattering system, and in it, the particle size is almost equal to the wavelength of radiation. Wavelength of radiation. The particles may be dust, moderate sized dust particles, pollen grains, smoke, aerosols primarily, or water vapor. So, Mie scattering occurs mostly in the lower portions of the atmosphere, where larger particles are more abundant. Okay, so the condition is that the particle size should be more or less similar to that of wavelength, and that is primarily available only in the lower part of the atmosphere, and it dominates when cloud conditions are overcast. I will just write it up. So Mie scattering occurs primarily in the lower portion of atmosphere. And why does that happen? It's because uh, the larger particles are present in the lower atmosphere portion itself, where larger particles are present in abundance, because that is a necessary condition for Mie scattering, and dominates when cloud conditions are when sorry cloud conditions are overcast. Okay, another thing is that me scattering does not differentiate between the different wavelengths. Rayleigh scattering does definitely does. I mean, as you can see from the inverse fourth power relationship with respect to the wavelength, but me scattering does not differentiate between the wavelengths, and hence it scatters all the wavelengths at the same, resulting in equally scattered white light from the sun. Since we see clouds as white, so that is an implication of it. The third type of scattering mechanism, which was asked in the question, was the non-selective scattering mechanism. So, for non-selective scattering, the particle size, the necessary condition is that the particle size should be much larger than the wavelength of radiation. So the particles can be water droplets and large dust particles, very large dust particles. The dust particles may have variable sizes. So in this case, the dust particles need to be very large. And why is it called non-selective? Why non-selective? Why this name itself? So this is non-selective because it does not select between the different wavelength ranges. I mean, it does not selectively scatter a particular wavelength range more than the other. So that is why it is termed as non-selective. Non-selective because all wavelength are scattered about equally, and this is the reason why you see fogs, causes fog and clouds to appear white in color, appear white as the blue, green and red color are all equally scattered. And what happens when these three colors are scattered equally? If blue plus green plus red are all scattered equally, then we will basically get white color, and that is why we see that the foggy conditions as well as the cloudy conditions are whitish to us. Human beings. That is what happens in non-selective scattering. So primarily the particle size is much larger than that of the wavelength of the radiation, and it is observed in water droplets and large dust particles only. So the question was, okay, non-selective scattering occurs when the size of the molecule is uh, much greater than the wavelength involved. So it has to be option D. Finally, I will just try to, discuss about a few advantages and disadvantages of satellite imagery. So you may have enrolled in this remote sensing course because of some particular reasons. Uh, Maybe because it is trendy, maybe because your seniors have also taken this course, maybe because this course is taught in your colleges also. There may be different reasons. Maybe you are interested. You are interested in the domain of remote sensing, or maybe you want to be an independent researcher sometime in this domain of remote sensing. So there may be several ideas in your mind while kind of enrolling into this course. But let's just discuss currently about the advantages of the satellite imagery system, and are there any disadvantages also? And if there are disadvantages, then let's discuss the disadvantages also. Okay. So the primary advantage of remote sensing based system is that advantage. The first advantage and the most important one is that it gives you a synoptic view. The satellites are present in the space, and they can basically receive radiation from a large area. So through that you get a large area coverage. For example, the three major satellites which we discussed today, the two major satellites which we discussed today, they were the MODIS satellite system or the Landsat satellite system. They give you a coverage of Earth. A global coverage of Earth. They give you a knowledge of the entire globe, primarily. MODIS gives you the coverage after every 8 days, most of the cases, whereas Landsat gives you coverage after a particular amount of days. So the coverage is very vast. It is very fine, and that is why and the Landsat coverage is primarily 30 meters at the spatial scale. MODIS coverage is mostly 500 meters. I'm just comparing among the two most common satellite systems, which is used worldwide among the remote sensing scientific communities. So the first and the major advantage of remote sensing or satellite imagery is that it gives you a synaptic view. The second one, it gives you an information about very remote or highly inaccessible areas. Okay, let us suppose you want to know about the melting of the glaciers in the Karakoram range, or let us say you want to know uh, about the forest health present in a remote island in Andaman and Nicobar. So definitely going to such remote places is not, something which we can do, all the time. So in such cases, the remote sensing based satellite imagery systems, they do help us a lot. You can perceive information about a location which is even quite inaccessible or highly remote. That is the second advantage of it. The third advantage can be that human eye can only detect wavelengths in the range of zero point 0.4 to zero point 0.7 micrometer, whereas satellites work uh, well beyond this range. So you can get knowledge about systems which are not even visible to us human beings through satellite imagery systems. Okay, so I had basically pasted a photo in the initial part of our presentation today. Yeah, so you primarily, can only perceive wavelength in the visible spectrum primarily from zero point 0.4 to zero point 0.7 micron. But what about the massive range of wavelengths beyond this tiny range? That of course can be detected only by remote sensing based satellite imagery systems. We human beings only interpret them and then we show it in the visible format to others. Okay, then number 4, you can also detect the temporal variation of a location. The temporal variation can be, let us say, diurnal, it can be weekly, it can be monthly, it can be annual also. So, it's not possible for a human being to go to a place and take observations at such a fine scale or for quite a long period of time. Always. So, the remote sensing based satellites do help us in our case. So, through this, you can also detect the landscape changes in a location. Landscape change. You can also understand the long-term urbanization. For those who are interested in urban planning and everything, you can also understand about the deforestation. So these are the primary advantages of remote sensing. There are a few more advantages. I will be discussing it now. Yes. So the fifth advantage is that you can even locate floods and fire through satellite imagery system. So you can, through that, you can map the extent of disaster. Obviously, it is not possible for human beings to go in such dangerous, I mean, disaster prone areas where it is completely flooded, or where there is a massive fire. So remote sensing would basically help us to understand the frequency as well as the aerial extent of such disasters. And remote sensing is a non the next advantage is that it is a non destructive mode of taking images. For example, in case you want to know, let us say the uh, the gross primary productivity, which is basically nothing but the net photosynthesis, the photosynthesis from a particular ecosystem. So usually, how we calculate it is by chopping up the plant and then calculating it biomass, and through that we get an estimate of the photosynthesis, the temporal estimate. But that is a destructive estimate. Through this remote sensing based approach, we would be getting to know about the let us say the fluorescence, or let us say uh, the the reflectance from the vegetation, and through that we can indirectly map the photosynthesis also from vegetation. So these are the six advantages. The next advantage is that uh, through three separate bands, as I was telling you, of images, various color composites can be produced. Composites for area of interest can be obtained, which will ensure that we get more details about the object or phenomena which we are actually investigating. So that is the thing. Through a single band image or through an aerial photograph, uh, you will be getting only a one band mostly. Okay, so but remote sensing based images can, through that you can even produce colorful images from the bands, the 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 wavelength bands which are not in general visible to human eyes. So that is one of the advantages too. Now let's just think about the disadvantages of remote sensing. Are there disadvantages also? And that is why I put a question mark in front of disadvantages, by the way. Because remote sensing is a widely used phenomenon, and many people forget that it has certain caveats also. I mean, it is not all uh, hunky dory. There are some missing elements to remote sensing too. Let's list them in the next slide. Yeah, so there are a few disadvantages of remote sensing also. The first is that certain skills are required to interpret the imagery. I mean, you need to employ some sort of skilled labor to do this kind of analysis. It is not completely skillless. It requires a certain amount of skill, and that is why I mean, most of us probably, I mean, most of you probably might have enrolled into this course to gain the skills required to understand about the earth sciences or urbanization or anything required relevant to your domain of interest. Secondly, we solely rely can't rely solely on satellite imagery, because satellite imagery definitely gives us some knowledge. I'm not denying that, but you need to back it up with some observational validation also. Validation also required. Number three, there are some powerful active remote sensing satellites which mostly work in the microwave range of electromagnetic spectrum. They emit their own microwave signal, and these signals can be quite intrusive, and they may even affect the phenomena investigated. The fourth disadvantages may be that uh, satellite image analyzed may be interfered interfered or distorted by other phenomena that are not measured. I will tell you an example in the next slide. So let us suppose you want to know the extent of a lake. Okay. Let us suppose, I mean, there is a lake, a water body, a large water body. Let us suppose it's a lake in a humid place like, let us say, Guwahati. Guwahati is in Assam. Okay. So you want to know the extent of the lake. So what would uh, the satellite primarily sense? It will sense the reflected radiation which is coming from the water, and then through some classification algorithm which you will be learning towards the end of this course, you can classify that piece of land as water. Okay, so lakes are primarily water land class. Okay, but what if there are algae? What if there are algae on the lakes? Algae would make the lake look completely greenish. Algae or water hyacinth. And mind you, the spectral signature or the spectral information uh, is very different for that of a water body than that of a vegetated surface. Let us say algae or water hyacinth. So due to the coverage of algae, dense coverage of algae or water hyacinth, the remote sensing based classification algorithm may misclassify this region as a vegetation system than that of a water system, and due to that, there may be a problem in the remote sensing based classification results. So that is what I was trying to explain. Finally, the fifth disadvantage which I can count off is basically that only knowledge can be obtained through Atmospheric windows. Atmospheric windows are the ones where, we can fairly see that the radiation at the top of the atmosphere is being transmitted to the land surface. Okay, so the results may be unreliable in some cases. Results may be unreliable. So we are done with this. Moving to the last part of today's discussion. The last part actually evolves from one of the problems which I took practically, I think 4 years back, and that is something very interesting. That is why I wanted to discuss it with you, because this course, remote sensing, is primarily more application based than theoretical. So I hope it would be fun to learn also for you guys. But yeah, so let me just take it up. Just a second, please. Am I? Yeah, it is being recorded. So let us just think of a scenario. Let us just suppose that you are a scientist in the National Remote Sensing Center, NRSC, ISRO, and you are making a mosaic of several satellite images. So does it have some disadvantage also? What do you think? Just to give you an idea, mosaic means, the remote sensing images will be like this. There may be some overlap. Okay, so this may be like this, and let us suppose you are trying to build a mosaic. Let us suppose you want to learn about the land cover. You are a scientist who deals with the terrestrial land cover estimation. You are currently employed in, let us say, an agency like ISRO, and you want to know the land cover. What would happen in that, in many of the satellite images, if you even download the Landsat based images from the USGS website, you will observe that many of the satellite images may be not so clear because of the cloud coverage. So one of the image may have cloud here, one of them maybe having clouds here or some other places. So what scientists usually do is that they have several images. First of all, they combine several images which are cloud free, and then they link them up edge by edge to produce a single image of a very large spatial extent, which is completely cloud free. So for image number one, let us suppose we name them as image number 1, 2, 3, 4, 5, 6. The image one may be from let us suppose March 1, because March 1 for that image 1 region was cloud free. Image 2 may be from March 13. Image 3 may be from, let us say, February 28, and so on and so forth. They may not be from the same date exactly. Why? Because we are just trying to remove the clouds, because clouds will not let you know what is inside and what is the land cover which is underneath the clouds. Okay, so you want to produce the cloud free images, and that is how you are doing. You are mosaicing the different images, maybe from different temporal periods, to produce a single large image which is completely cloud free. So that is the mosaicing thing. So does it have any caveats? Does it have any drawback? Yes, it also has some, has a list of drawbacks. I will explain it in the next slide. So the list of drawbacks are: number one, if the images obtained are taken at a different tilt angle of the camera present in the satellite, then there can be certain aberrations in the image. Okay, so in order to explain this, I will take another slide. So let us suppose in one of the cases, which is nadir. Nadir is something, in remote sensing based nomenclature, in case you are basically analyzing a body from the vertical point itself, right from the top itself. So that is nadir. You will understand this nomenclature, in due course of time. And it is off nadir if you are analyzing something from not a vertical position. Okay, so in order to see this part from an off nadir position, you need to tilt the camera. You cannot keep the camera in the vertical alignment anymore. And if you tilt the camera, the tilt angle will be different as it is written in the first point in the satellite. Then there can be certain aberrations in the image. The off nadir images are obtained by tilting the camera, whereas the images obtained at nadir have minimal camera tilt. The perspectives of both these images are expected to be hugely different. There should be some correction applied to the images before forming their mosaic. So that is the first probable caveat of this mosaicing system. So you need to apply some correction factor before mosaicing it. Okay, so that is the first step which you need to be which needs to be taken. Number second, if the region of interest is land, then the clouds present over it can hinder the electromagnetic radiation from the land. The mosaic of such cloudy images will not be an accurate way of depicting the land below the clouds. So you need to produce land-free images, I mean cloud-free images, sorry, uh, for each of the mosaic images. Number three, the different satellite images can be taken at different time periods. I mean, the one which I told about cloud-free mosaic systems. It is not certain that the illumination from the sun will be constant for all the images, and hence there will be difference in the intensities of colors of the overlapped regions of two images. This may cause a problem in the formation of mosaic of these two images. So, what may happen is that you are moving through an aircraft over a region. Okay, and for one of the images was taken at, let us say, 10 a.m in the morning. One was taken at 12 noon. So the illumination will be very different. Illumination will vary diagonally. The illumination will even vary with respect to the seasons. For example, in general, the monsoon illumination is lower because of the cloud coverage, of course, of the sun, whereas the illumination is higher during a cloud-free sunny day. So the illumination will also change. So it is not certain that the illumination from the sun will be constant for all the images, and hence there will be difference in the intensities of colors of the overlapped area of the two images. This may cause a problem in the formation of mosaic of these two images. The two images, the fourth point is that the two images which are to form a mosaic should have the same spatial resolution and radiometric resolution to maintain uniformity of the features. So spatial resolution, in case you don't know about it right now, it is basic. Spatial resolution is the size of the uh, most basic fundamental unit of any image, which is known as pixel. So that is basically spatial resolution. So if the size of the pixel is 30 meter by 30 meter, then the spatial resolution will be 30 meter by 30 meter. And the radiometric resolution specifies that how many grayscales are there in a particular image. So if it is an 8-bit radiometric resolution image, then that would mean that there are 2 to the power 8 grayscales. That means that there are 256 grayscales in the image. So you need to ensure that the spatial resolution as well as the radiometric resolution are the same for mosaicing of the images, just to ensure that there is a uniformity of the features. And lastly, due to the noise caused due to aberrations in electronics which are placed in the satellites, moving parts, and defects in the scanning system of the satellite, images may lose some spectral features. The mosaic formed by such images will not give a real presentation of the area of interest. So that is the last part which I wanted to discuss for today's course. So we learned a lot today, by the way. We started our learning by taking up a few courses, a few questions. The first question was about active versus passive remote sensing based approaches. We learned about the different passive remote sensing satellites also. We also learned about the different active remote sensing based satellites also. The second question was about an example of a remote sensing. The fundamental is that in remote sensing based approaches, we don't actually touch the object or phenomena which is being investigated. The third question which we took up was about the atmospheric windows. So atmospheric windows are only those uh, wavelengths through which the energy can actually penetrate sufficiently for detection. Okay, and this window is due to the presence of several atmospheric constituents like the molecules or the dust particles, the water vapors, or some greenhouse gases, which are the constituents of the atmosphere. So this is this absorption. This is basically due to the absorption. Next up, I also took up an example of the energy budget of the Earth. So uh, we saw that how much of the extent of the total solar irradiance at the top of the atmosphere can actually get absorbed by the atmospheric constituent. It's a massive amount, by the way. Then we also learned, through a question, the electromagnetic spectrum wavelength range for microwave radiation. We also got to know that there is a massive wavelength range, which can be utilized by several different remote sensing based approaches. The human beings can only detect a very thin wavelength range, which is from the zero point 0.4 micron, which is blue spectrum, to 0.7 micron, which is towards the red spectrum. Then, in the fifth question, which was discussed today, we understood about the three fundamental laws of remote sensing: the Wien's displacement law, the Planck's law, and the Stephen Boltzmann law. We understood that the Stephen Boltzmann law plays a paramount role. It detects the amount of radiation which is emitted by a particular body per time per unit area, and it is directly proportional to the fourth power of the temperature. So, as the temperature rises, the emitted radiation will actually rise massively. Then we took up a question about the polarization. We took up all the different kinds of polarization approaches: linear versus circular versus elliptical. In linear, we understood the vertical polarization system, horizontal polarization system, and the slant polarization system. We also learned about the circular polarization systems. We also understood that they will be also dictated by the antenna, the placement of the antenna, and the energy emitted by it. We understood about the right hand and the left hand circular polarization and elliptical polarization approaches. Okay, in circular polarization, the radio wave is rotated as the signal propagates, and in elliptical polarization, the electrical field is propagated in an elliptical helix. Okay, so that is why these names come to be. Then we took up a question on the coherence of these two waves. We understood which two waves can be termed as coherent. They need to have some particular phase difference. The phase difference may even be zero, but that needs to be constant. First of all, they need to be monochromatic, which is not the presence of a particular color, but the presence of a particular wavelength. Because color is extremely subjective in this course of remote sensing. Your perception of color will change by the time you end this course of remote sensing. I'm definitely saying that. Finally, we took up a question on the Doppler effect. Doppler effect, primarily they use sound waves. And then we took up five different cases. The fifth case actually was the one related to our question, which was discussed today, when both the source and observer were moving, and they were moving towards each other. We observed that in such a case, the shifted wavelength will be actually shorter than the original wavelength, and the frequency will show the opposite relation, because the frequency and the wavelength are inversely proportional to each other. Finally, we understood about the different scattering mechanisms. We understood that the radiation interaction with the atmosphere primarily occurs through absorption as well as scattering. And we understood about the three different scattering mechanisms: the Rayleigh scattering, the Mie scattering, and the non-selective scattering. They are primarily determined by the particle size and the wavelength of the radiation size. If the particle size is much smaller than that of the wavelength of radiation, then that's Rayleigh scattering, and due to that, we see the sky to be blue. And why do we have a red color in the traffic signals? It is because the red color is scattered the least among the visible wavelength, and that is why you would be able to detect it well, even in foggy conditions or even from a particular distance. Okay, so that was about the Rayleigh scattering. The second scattering type was Mie scattering, in which the particle size is almost equal to that of the wavelength of the radiation. And the third type is the non-selective scattering, where the particle sizes are much larger than that of the wavelength of the radiation. And it is termed non-selective because they basically because it scatters all the wavelengths almost equally. And since all the B, G, and R, I mean blue, green, and red bands are equally scattered, so that is why we see uh, the resultant non-selective scattering phenomenon to be primarily white. That is why we see the foggy conditions to be white. That is why we see we observe the clouds to be white in color. After that, we discussed about a few advantages and disadvantages of remote sensing and satellite imagery. So, I mean, there should be a caution. That is, I mean, the basic funda out of takeaway should be that remote sensing approaches help the human beings a lot, definitely. But of course, I mean, there needs to be. I mean, we need to take a particular amount of caution also in gaining knowledge about remote sensing based interpretations. You need to read the results from remote sensing based interpretations with a pinch of salt, probably. And finally, we took up we just discussed a case of mosaicing of several satellite images and their probable caveats. We understood why there may be maybe some faulty results through mosaicing also. So that was the end of this first weekly live session. We will meet again the next Friday. I will be meeting you every Friday from 6 to 8 p.m. Uh, Please feel free to ask me anything. If there is any question, please feel free to ask me. Please go ahead and ask me if there is anything, any doubt or anything related to that. No question at all? Okay, I take it as no question from you. So we shall end this first weekly live session. We will meet again from 6 to 8 p.m. Yeah, do you have any question? Kodimala Rishwar?
Yes. Hi, Abhishek. And I am the teaching assistant of this course. And that's why I was keeping quiet all the
Okay,
way.
okay.
So the session was quite informative. And I appreciate your efforts.
Okay, thank you.
Nice job. Keep it up. Carry on.
Okay, thanks.
Thank you.
So I think we shall end this live session. We'll meet again the next week on Friday from 6 to 8. Thanks a lot for joining.
Thank you.
Thank you, everyone.